Hi everyone. Hi everyone. Welcome to AWM Pitt Grad Seminar. Today we have two speakers. The first speaker is Bilyana uh, Tzolova, and she is PhD student from Rice University. And her talk is modeling the flow and transport of the TACE treatment in the liver organ. And our second speaker is from China. Her name is Lei Wei. She's PhD student from Huazhou University of Science and Technology in Wuhan. Her talk is the dispersion problem of the Schrodinger equation with magnetic potentials. And our first speaker, Bilyana, you can start.
Okay, can you see the full screen, the full presentation? Good, okay. My research, sorry, let me just move this. Okay, so my research is a joint effort between Rice University and the University of Texas MD Anderson Cancer Center. So the purpose of our research is to create a model for the flow and transport of chemotherapy treatments from liver vessels into the liver and the liver tumors, and to apply this model to data that we receive from MD Anderson for patients who have been diagnosed with hepatocellular carcinoma, which is a type of liver cancer, which we'll call HCC moving forward, and who have undergone transarterial chemoembolization treatments, which we'll call TACE moving forward. And the motivation of our research is to better understand these TACE treatments and to hopefully improve them in the future. So when a patient goes through a TACE treatment, the TACE is applied by inserting a microcatheter, and the microcatheter is then guided up to the liver, and a dye is then injected in order to highlight the vessels that lead to the tumor. Once those vessels are identified, the microcatheter is further guided to the exact vessels that feed the tumor, and the chemotherapy and embolic agent solution is injected. So that's what's pictured up here. The chemotherapy aims to attack the cancerous cells and to kill those cells, and the embolic agent will clog up the blood vessels in order to keep the chemotherapy at that tumor, and also in order to keep blood from flowing to the tumor, because the blood is what energizes the tumor and keeps it alive. So our motivation to study these TACE treatments, unlike other types of cancers, the incidence of hepatocellular carcinoma is increasing worldwide. And most patients who have this type of cancer don't have surgery as an option, which means that these TACE treatments are their only treatment plan. Because these TACE treatments end up clogging up some of the blood vessels in the liver, they can also end up clogging up blood vessels that supply blood to the healthy liver tissue. And as a result, patients can only undergo a limited number of these treatments in order to keep their healthy liver tissue viable as well. There are several different combinations of chemotherapy drugs and embolic agents that can be used for these treatments. And so far, it's unclear which one of these combinations or drugs have an advantage over any of the other ones. And it's also unclear whether the chemotherapy or the embolic agent itself is more effective in treating these tumors. So hopefully by being able to model these treatments, we can better understand these questions. So to begin with, we are given CT images of patients who have undergone TACE, and these CT images are made up of about 100 to 200 of these images here on the left. And the number of these images is dependent on the size of the patient's torso and also how far the images are spaced. And we can also reconstruct these CT images to view from the side of a patient and from the front. So a practitioner will go through all 100 to 200 of these images in order to label the liver, the tumor, and the vessels of the patient. So highlighted here in red is the liver of this patient. And then highlighted here in orange is the vessels of this patient. So as you can see, the vessels are a very small portion of the liver as a whole. So once we are given these segmentations, we can create a 3D rendering of these patients. So here are two different patients that we have from MD Anderson. Orange is the liver, in yellow we have their tumors, and in green are the vessels. So as you can see, there's a huge variety of geometry that we're dealing with, right? So some livers can be much larger than others. The tumor location can be in different places, and the vessels can stretch either horizontally and vertically, as you can see here. And the number of tumors can also vary between patients, and the size and structure of it can vary. So we have a very problem that's very dependent on the patient. So from these segmentations, we have decided to reduce our vessels into 1D models. This is because the vessels are much smaller than the domain in which they exist in, the liver, and this allows us to have a simpler model. So in order to reduce our vessels to 1D structures, what we're going to do is extract the center line of the liver vessels. So inside the liver, there's 4 different vascular structures. First is the vena cava and the venous system, and those are responsible for draining the blood out of the liver. And then we have the artery and the portal vein, which are responsible for supplying the blood to the liver. And because we want to pump chemotherapy into the liver tumors, and we want to block the blood flow into the tumors, we're going to focus on these latter two. And pictured here on the left-hand side is the 3D structure of the portal vein of one of our patients, and on the right-hand side is the 1D center line of that same structure. So this does connect outside of the liver, but since we're only interested in modeling the flow inside the liver, it does come out as 2 separate structures, even though it should be connected at one point outside the body. So in order to create this 1D structure, we're going to use the vascular modeling toolkit in 3D Slicer. So the centerline extraction that we get from this toolkit splits our vessel into segments at each branching point. So this vessel here is converted into 3 different branches, and it gives us the radius, the average radius for each of these segments. And we're going to use this later in our model, but it's important for us to have the average radius for each branch, because naturally we expect more blood flow through a thicker segment than through the thinner one. We can also specify the number of points that make up the center line of our segment. So if we want to reduce our computation time, we can say that this should only be 5 points rather than the about 20 that we see here. And note that we're going to call the whole center line lambda, and lambda I is going to be each center line that connects each set of points. So we are going to be solving the miscible displacement equations inside of our liver. And in order to do this, we are going to use the finite element method and discretize our liver and tumor segments into smaller tetrahedral elements. So this large 3D structure is going to become this mesh on the right. And this mesh is made up of about 12,000 tetrahedral elements. And to generate this mesh, we're going to, again, use 3D Slicer, and it generates it for us. And it also labels for us whether this is part of the liver in purple or whether it's tumor here in red. So we're going to treat it as one large mesh, but then we can know what's entering the liver and what's entering the tumor after the fact with our results. So the equations that govern our model are going to be the miscible displacement equations. And these, we define the displacement of blood and chemotherapy inside of this liver mesh omega, which is what I showed in the previous slide, over our time interval from 0 to final time t by the following equations. The first equation lets us solve for P, which is our pressure inside of omega, which is our liver. The second equation gives us U, the velocity of the fluid inside of our liver, so over omega, our liver. And the last equation gives us the concentration of chemotherapy that is inside of omega, our liver. The other variables that we have inside the equation, lambda, as we defined earlier, is our vessel centerline. And F is the linear mass flux, so what's entering through our vessel. And we're going to set that equal to gamma, just the coefficient, and R, the radius that we calculated earlier. C hat, which is in our concentration equation, is equal to the initial concentration that we are injecting into the liver. And T is our final time. We also have two other variables, our diffusion matrix, D of U, and K of C, our coefficient. And for now, we're just going to simplify those down to the identity matrix and a coefficient K naught. So that gives us the following simplified equations for flow and transport. So we're going to go through each of these in order to solve them. First, we need to solve for the pressure inside of our liver. And we note that we have this delta function for our center line lambda. So for problems where we have a small center line, we are going to end up getting a singularity if we're solving for the center line directly. So in order to avoid this, we're going to use something called the singularity subtraction technique. So this technique was introduced for problems where the vessel radius was smaller than the mesh size. So rather than refining the mesh around where the center line is located, we're going to define our solution F as the sum of two different terms. So our first term here is made up of a G, which is our Green's function, and this term here is going to contain the singularity that we would otherwise cause a problem inside of our solution for pressure. And because this first term contains the singularity for our solution, our second term, the correction term, is going to give us a standard elliptic equation that we can solve without any sort of problem. So the problem that we're trying to solve here is the following elliptic equation inside of, the following Laplace equation inside of our domain omega, where we have two different boundary conditions. So on the boundary of our liver, we want to set the pressure equal to 760 millimeters of mercury, which is just equal to the ambient pressure. And then anywhere on the boundary where we have a vessel entering, we're going to set it equal to 850 millimeters of mercury, which is ambient pressure plus average blood pressure. So this is our system of equations. And in order to use the singularity subtraction technique, we're going to plug our solution P, which is the sum of these two terms, into this equation 3 that we're trying to solve. So that gives us the following equation. So as I mentioned, the first term in our singularity subtraction technique is made up of our Green's function G, and we're going to take advantage of the property that the Laplacian of our Green's function is equal to our delta lambda function. So we can cross out the left-hand term up here with the second term over here, which leaves us with 3 terms, one of which is our correction term, which we want to solve for. So we're going to convert the problem for pressure into the problem for the correction term for pressure. So this equation comes from our previous slide, and then we're going to adapt our two boundary conditions so that the correction term, so the pressure is equal to 760 on the boundary, so our correction term should equal to, when you plug that into our singularity subtraction technique, the equation for W. And the same goes for our other boundary condition. And here we're going to let E of F be the extension of our linear mass flux from the vessel into our large liver domain. So when we solve this problem over our omega mesh, we get the following solution for pressure inside of our liver. So here in white, if you can see it, is pictured our vessel center lines. And we can see that the pressure inside of our liver varies from 760 to 850 and is higher right where our vessels are entering the liver, which is to be expected. So going back to our simplified equations for flow and transport, we've now solved for the pressure in our first equation, and so we can use the solution for P and plug it into our second equation for the velocity of the fluid in order to get out our value for U. So this can be solved for directly. And then we have our last equation, which is the concentration of chemotherapy inside of our liver. So once again, with this equation, like with the first one for pressure, we have a delta function here. So to avoid singularity like before, we're going to again use the singularity subtraction technique to solve the time-dependent advection diffusion equation. But we have a few more challenges that we didn't have before. First, we need to account for our initial concentration C hat, which we didn't have in the previous equation. This equation, unlike before, is time dependent, so we need to deal with that term. We have several options for what we can use for our Green's function because we're no longer using the Laplacian equation. We now have a advection diffusion equation. And in situations where we have an advection dominated problem, we could experience some numerical instabilities. And one more thing to note here, on the boundary here, we want the concentration to equal to 0 because we don't want any chemotherapy to be on the boundary of our liver. So to account for our initial concentration, we're just going to adapt our splitting technique so that our singularity term will be multiplied by our initial concentration C hat. So this allows us to eliminate our delta lambda function easily. So that was a nice solution and we can move past it. Now for our time-dependent problem, we're going to have to discretize our concentration in time, where Cn is equal to the value of our concentration at time n tau, where tau is our time step. So we're going to make an approximation for this derivative. So since we're applying the singularity subtraction technique, there's two methods that we could take here. We could either first discretize in time and then apply our singularity subtraction technique, or we could apply our singularity subtraction technique and then discretize in time. This will give us slightly different equations for our correction term. Most notably, we're going to have a different time derivative. So our initial concentration is going to be different from what we use in the two different methods. So we're going to solve for our correction term and for our concentration inside of a unit cube, just for a basic example where we know what our expected solution should be. So here we have a unit cube and just a straight line down the middle, which is follows basically the solution that is inside this unit cube. And when we look at our solutions using our two different methods, they look pretty similar. It's pretty hard to tell which one is doing a better job, and the range of them is about the same. So in order to figure out which one is closer to the actual solution that we want, we're going to calculate our relative errors and then our convergence rates. So we expect a convergence rate of about 2 for both of these problems. And we see that our method 2 gives us better errors and better convergence rates. So we decided to move forward with method 2, where we apply the singularity subtraction technique first and then do a time discretization. Okay, so going back to modeling our concentration, we've accounted for these first two problems. We explored several different options for our Green's function and decided to keep using the Green's function for the Laplacian equation because it would still contain our singularity for the time for the advection diffusion equation. And also to avoid numerical instabilities, we decided to use discontinuous Galerkin elements instead of continuous Galerkin elements when we're solving for our concentration. So the correction term for our concentration at time n tau is given as follows. Here again, our boundary value is going to be so that our concentration is equal to 0. Our correction term just has to balance out with the first term that captures the singularity. And we're going to have to set an initial correction term for our equation, and this is just going to be the same thing relative to C hat, our initial concentration. So we solve this again inside of our unit cube and get a nice solution, which is between 0 and 0.64 for our concentration. So now we've solved for all three of our equations inside our miscible displacement equations. And as you may recall from the beginning, we made some simplifications that we're going to add back into our equation. So we're going to add back in our K of C coefficient here, and we're going to add back in our diffusion matrix D of U. So because we're adding this back in, our first equation depends on our solution for our for the concentration C, and our concentration C depends on the solution for pressure because our diffusion matrix depends on the velocity U. So we're going to do a time lag when we're solving for our pressure and our concentration. They're going to continuously update over our time interval. So when we do this, when we couple the flow and transport equations, we compare it to a known solution, we get the following relative errors. So as our mesh gets finer, we see that the errors are decreasing, which is what we wanted for both pressure and our concentration. And again, our convergence rate is close to 2, which is what we want, something that's decreasing with time, with the mesh size. So far we've modeled the flow of the blood and the flow of the chemotherapy. But the last component of the TACE treatment is when the embolic agent is injected, which plugs up the blood vessels. So to do that, we are going to change our model so that after the point of injection, the blood flow is decreasing with time. So we're going to let the black vessels here be vessels that are not affected by the embolic agent. And the red vessels here are going to be governed by the following equation, where alpha tells us that the flow inside that vessel decreases with time. So initially, we'll have full flow going through that blood vessel. Then at halftime, we're going to have half flow, and maybe you can see that the pressure is decreasing along that branch. And then at the end, we should expect no flow through that vessel. It should be completely clogged up, and the pressure is down to 730 millimeters of mercury there. And we evaluated it to see what the pressure is along this red line here. And as you can see, it dips as we go from full flow to half flow to no flow along that red line. So in summary, we are able to model our coupled flow and transport equations. And we've shown that we can use the singularity subtraction technique for our advection diffusion equation. And our future work is to apply this full model for the coupled flow and transport equations to the patient data that we got from MD Anderson, and to evaluate how this TACE affects our patients. So happy to take any questions.